All right, in this problem we have two parallel wires that have currents running in opposite directions, and they're hanging from these hooks, and they have this wire that goes up and over and back down to the other side. Total length of this wire is 16.2 centimeters. The mass of the wires of these lines carrying the current is 30 grams per meter, and we know that the angle between the vertical and so I complete this triangle here and just draw a line straight down. We know that that angle is 5.89 degrees. We know that if we go up and down, that distance is 16.2, and we know the mass per unit length out here is 30.8 grams per meter, right? And so we're asked, what is the current that it takes to put this in equilibrium? And the key issue is this is in equilibrium, and it's in equilibrium between the magnetic force and the gravitational force. All right? So let's take a look at first what the magnetic force per unit length is. Well, between two parallel lines, the magnetic force per unit length is mu naught I1 I2 over 2 pi r. In this case, there's only, the currents are equal, so we can write this as I squared over 2 pi r. All right, we don't know r, but we have everything we need to know r, to figure out r. Because if we look at this triangle again, all right, I'm just going to draw it so that we're straight on. All right, if we look at the triangle, okay, there, drop a line straight down, we'll pretend that's straight. That angle is 5.89 degrees. I'm just going to call it theta. This length over here is half of the length of the line, the cord going up and over. That total length is r, so this side is r over 2. Right? And so we're at sine theta is r over 2 over L over 2, right? Opposite over adjacent. And so we can get r, we simply get r is L sine theta. Right, so I'm going to write that right here. R is L sine theta. Okay. So the key issue here is the magnetic force and the gravitational force are in equilibrium. So let's zoom in on this again and think about it. So I've got my line coming down like this, right? We know this wire is not moving, it's in equilibrium. We know gravitational force is mg, right? Well, gravitational force per unit length would just be mg over L. And we know we have an equation here for F over L. Right? So what's true when these are in equilibrium? Well, we can break these two forces into a component that is along that wire, because any forces in alignment with that wire are just gonna, and you got to remember the two sides are equal and opposite, right? So any forces in alignment with the wire are just going to cancel out through the wire, and that's no big deal. But then each one of them has a component that goes perpendicular to the cord, right? Each one of them has a component that goes perpendicular to the cord. So we have to look at what are our triangles, where are the different angles involved, and how do we get to that relationship where this component of mg over L equals that component of F over L, right? So what is this angle? Well, that angle is theta, right? And what is this angle? That angle is minus theta, and that means that angle is theta. Right? Why do I say that angle is theta? Are these angles? There's theta. right? There's theta. Theta is the angle between the vertical and the line. Well, here, this is the line, that's the vertical, so theta is there. If that's theta, this and this are perpendicular to each other because F over L is straight away from the other wire. MG is straight down. That's 90 minus theta, or pi over 2 minus theta, which means this, since this is perpendicular to that, this is also theta. All right, so we have mg over L here, we have theta, and we have that component. That means this, right, which is what we're after, this is related to sine of theta, right? So if I took mg over L sine theta, sine theta, right? mg over L sine theta, that's this component right there, right? Over here, it's F over L. Well, here, it's the adjacent angle, right? So on this side, it's F over L cosine theta, right? So what we have is F over L cosine theta has to equal mg over L sine theta, right? So let's go back and write that. We have F over L cosine theta, right, is mg over L sine theta. And since we know mg over L, we need to solve this for F over L, and what we get is F over L is mg over L sine divided by the cosine of tangent theta, right? mg over L equals tangent theta, equals, right, u naught I squared over 2 pi r, right? mg over L, Okay, so we have mg over L tan theta equals mu naught I squared over 2 pi r, and we know r is capital L, our capital L sine theta, and so mg over L tan theta mu naught I squared over 2 pi L sine theta. And we need to solve for I, right? Because that's what we're after. What current? So I squared is 2 pi L sine theta onto mg over L tan theta, and all of that 1 over mu naught. Okay, what do we know? We know L, right? We know that L is 16.2 centimeters. We know theta. Theta is our 5.89 degrees. G is 9.81. M over L is 30 grams per meter, which you'll need to convert to kilograms, right? You'll need to convert 16.2 centimeters to meters. You need to convert 30 grams per meter to kilograms per meter. And that gives you everything in this equation. And that's it for this problem. Oh, and we take the square root. My apologies. There we go. And that's the answer you're looking for.